Good morning, good afternoon, wherever you may be in your day. Thank you, as always, for choosing to make chemistry part of your day. Take two. This is going to be a two-parter. First part, we're going to do concepts. Second part, we're going to do math. Try to break it up, make it a little bit shorter. So without further ado, let's get into the concepts. And admittedly, this next slide is going to be confusing and have a lot of information that we've got to think about here. So let's hit it. Three definitions that are really all the same thing. The difference is really subtle, and it's in the units, and it's going to end up with three different ways of mathematically treating these situations. So we do have to be careful in what we're looking at. And I'm not actually as worried about the definitions as I am symbols and units, and really units. The units are going to save you, as always. Let the units be your friend. Let them tell you what you're going to do. Before I get into the definitions, let me do one more thing up front. Change in temperature. So anytime you see delta, that means change, and it means final minus initial. So if it's negative, it means the final is smaller than initial, or something got smaller. If it's positive, it means the final is greater than the initial and went up. So again, hopefully those are intuitive things, but delta means change, final minus initial. Big T is temperature, so that would be your final temperature minus your initial temperature. The change in degrees Celsius is identical to the degree change in Kelvin. If you don't believe me, let me just do a quickie demonstration. So if I took 5 degrees Celsius minus 1 degree Celsius, we all agree that's 4. Remember, our conversion factor is to add 273 plus the degree Celsius will give us our Kelvin. So 5 plus 273 gives me 278. 1 plus 273 gives me 274. And 278 minus 274 is 4 as well. So again, this doesn't matter what temperature I change. You're adding 273 to both the beginning and the end, or subtracting 273 from the beginning and the end, so it cancels out. So just remember, Celsius, Kelvin will be the same. So when I see a unit like joules per degree Celsius, somebody also could write the same way, joules per Kelvin, and that'd be fine. You could also have kilojoules. So again, the units get a little bit jumbled up on this chapter depending on what part you're in. Sometimes you use joules, sometimes kilojoules, sometimes Celsius, sometimes Kelvin. So just read carefully. Let the units tell you what you should do, and cancel out the units as appropriate. Okay, so let's get into these different definitions that really aren't. Heat capacity. This is the ability of something to retain heat, maintain temperature. That's kind of conceptually what it is. Textbook-wise, it's the amount of energy needed to raise 1 gram of an object 1 degree, that's the next one. This is why this is take 2, by the way. The heat needed to raise the temperature of an object 1 degree. Not to be confused with specific heat capacity, which is almost the same definition, except now it's not an object, it's 1 gram of a pure substance, such as water, glass, copper, sand. You get the idea. So, you can see the confusion here. And to help with that confusion, we've used capital C and little c as the symbol, which admittedly in handwriting on a board looks awfully similar. Maybe even identical, you might argue. So again, I'm not as worried about the words, I'm not as worried about the symbols, I am as worried about the units, because it's really the same thing, because you can add up the specific heat capacities and build an object and get the total heat capacity. So they're related to each other. This one is dependent on how much of the stuff we have. You can tell because it's got grams in it. This one is just the entire object by itself, and it's a repeating object because there is no mention of mass in it. So that's the big difference. Does mass matter? If mass matters, pure substance, specific heat capacity, or sometimes just called specific heat. And that probably does help to drop the capacity. Heat capacity is the whole object, conglomerate, whatever you had. So this might be your water plus the beaker it's in. Or a thermometer in the solution with the beaker. So all of that together could all be rolled together into the heat capacity of the whole system, which is what we're studying. And in chemistry class, that's the chemicals, review from the last one. Okay, so heat capacity, no mass, it's for an object. Specific heat, pure substance, 1 gram, the amount matters. So substance, 1 gram, object, it's an object. It has whatever mass it has. And look at the units. So joules per gram degree Celsius, joule per degree Celsius. Celsius and Kelvin are interchangeable in this. And then one last version of the same thing, just to add a little bit more confusion on. Typically a C with a little p subscript. So this would be the molar heat capacity. So this is the energy needed to raise 1 mole of a substance 1 degree Celsius. So, of course, we can convert between these final two using formula weight. So we just got to do a gram per mole calculation. Now, if you do this, make sure you're careful because that gram's on the bottom. So, you got to multiply by the formula weight to get there. Okay, I think that covers the definitions here. Let's do a little bit more conceptually before we get to math. Let's look at our units a little bit more closely. First of all, let's introduce this idea of our energy unit, which is actually it really starts with the calorie. So the calorie is defined as a specific heat of water. So that's the amount of energy it takes to raise 1 gram of water, or 1 milliliter of water, 1 degree Celsius. Remember, the density of water is 1. Now, this is not a standard unit. This is not a metric unit. So the metric unit is joules. So 4.184 joules equals 1 calorie. If you look, this number is on the back page of your test as one of your constants, so you don't have to memorize it. It'd be nice if you did enough problems that just kind of got stuck in your head organically. And if we multiply each side by 1,000, which remember, you can do that in math. It doesn't change our equal. So 4.184 kilojoules equals 1 kilocalorie. And why do I bring up the concept of a kilocalorie? Well, a kilocalorie is actually your dietary calorie. So when you see calorie on a label, it should be capital C. Little c is this calorie. Big C is this calorie. So it's a difference of 1,000. So when we start talking about these fundamental scientific units versus, everyday usage of the word, once again, everyday usage has changed from the actual scientific principles. So just to make you aware of that. And 1,000 little calories is a big calorie or a kcal. So same ideas. Remember, conversion from kilojoule to joule is the same as kilometers to meters or kilograms to grams. So same metric system use over and over again. All right, so let's look at these whole ideas. So heat, our symbol is going to be Q, our unit's going to be joules or kilojoules, and we want to look at these different versions of capacity that were on the board previously. And let's just look at these units. So we got joule, gram, Celsius. So if we want to relate heat, which is joules, to C, which is joules in grams and Celsius, we got to get rid of grams, which is a unit of mass. Very good. We have Celsius, which is a unit of temperature. Very good. So if we put all this math together, we see that our heat equals our specific heat times the mass times the change in temperature. And again, if you just do this so the units cancel out, you're going to get the right answer. But this is going to be what I like to call Q for pure substance. Then we have the big C, which is joules per degree Celsius. So all we have to do is get rid of that temperature on the bottom. So it's just big C times delta T. This is what I like to call Q of an object, in trying to simplify these terms. And then you have the molar heat capacity, where it's going to be the joules per mole degree Celsius, in which case N is our symbol for moles. I don't think we've used that yet in any of the videos. So we have the molar heat capacity times our moles times our change in temperature, and that'll give our heat change here. I do less of this, to be honest. Most of the examples I work and what I'll give you in class, or work in class, on the homework, on your tests, is really going to be in this realm. But I did want to put this here. Honestly, if I was using this, I would just convert from moles to grams and then use this just like we used everything else. Instead of trying to learn another equation, I would just go from moles to grams because we've done that a whole bunch. So that idea. Okay, so what does this tell us mathematically matters for the changing of temperature of an object? It really tells us 3 things matter. One, a lot of these things probably make sense. The energy change is associated with how big a temperature swing we have. So if I touch something that's warm versus a hot stove, that difference in temperature matters, right? Duh, of course. The amount of stuff I have matters. If I have 1 drop of hot water, probably not going to burn my skin. If I drop a gallon of boiling water on my hand's probably in very big trouble. So again, duh, obviously amount matters, but just to point this out, the range of temperatures matters, the amount you have matters, and then all substances aren't equal. Aluminum is different than copper, which is different than iron, which is different than water, which is different than air, which is different than your skin, or my glasses, or anything else. So I think these are kind of obvious things, but I do want to point out these are the 3 things that matter for changing for heat flow. And then one last piece of demonstration. Pause this for a second, go grab a spoon or something made out of metal, and grab something made out of paper, and come back and hold them both in your hands. And do they feel like they're the same temperature? Well, they're in this room. They're sitting at what I'd call ambient temperature, room temperature. They're the exact same temperature. Why do they feel so different? Well, they feel so different because they have different heat flow, they have different capacity. That identity matters. You're warmer, hopefully you're not sitting in a sauna watching this, but hopefully you're warmer than the room you're in, right? Body temperature, 96 degrees. Hopefully your room is cooler than 96 degrees, 97, 98, whatever it is. 98 degrees, in which case heat is flowing from you, the hot object, to the spoon, which is the cold object, and the book, which is also the cold object. They're the same temperature, but what's different is their ability to absorb heat. So it feels like the spoon is colder than the book, even though they're the exact same temperature. You're looking at the difference in capacity and the amount of energy they can pull from you. So what does this look like mathematically? Good question. So two concepts I just discussed. You have a hot object and a cold object, touch. The hot object will get colder. The cold object will get warmer until they're both at the exact same temperature. And that's an important concept there. They will go, one will go up, one will go down until they're the exact same temperature. They won't move the same amount. You know this, on a hot day at the beach, the sand feels different than the water. Well, why is that? Water's got a really large heat capacity, and I don't have sand up here, but it's very low heat capacity. So the sand has very little ability to retain heat. It transfers it more quickly to your feet. It gets hotter faster out in the sun, and it gets colder faster at the end of the day when the sun goes down. So this is really a measure of the ability to maintain temperature. The larger this number is, the slower the temperature moves, and this is both heating and cooling in both directions. And it also is a representation of how much energy can be stored by that substance. So they're going to be able to give off more energy if it has a higher heat capacity. And I will say with the caveat of equal amounts. So water holds twice as much thermal energy as ice would at the same temperatures, although that's a little bit hard to do since water would freeze. But you could do it right at zero. Alcohol, again, is going to be less than water. If we go to something from, say, a fluid to a solid, notice these metals have relatively low heat capacities. Metals change temperature fast. If you ever, wrap some bread in aluminum foil, throw it in the oven, pull it out. The aluminum foil cools down pretty quick. Within a matter of a minute, you can probably touch that aluminum foil with your bare hand and not hurt yourself. And it's because that heat capacity is very low, so it gives off the heat quickly because it didn't absorb that much heat in the first place and gets back to room temperature. And even if it is warm, your hand can absorb a lot more heat than the aluminum foil, so you're okay. Have that insulation idea. And I think this is it until we get to the math. So I'm going to cut this video, and we'll come back and apply this in some traditional word problems. Thank you so much, and excited to see you on part 2. See you on the other side.